At a quiet point between Earth and the Sun, far beyond the noise of cities and the limits of ordinary vision, a new kind of space telescope unfolds. Thousands of mirrors drifting in perfect coordination, capturing fragments of light that have traveled across unimaginable distances. These reflections converge into a single image, and for the first time, humanity sees something that feels both distant and strangely familiar. A faint blue glow, streaks of green, subtle patterns that resemble coastlines and continents. There are hints, just hints, of oceans, land masses, perhaps even structures that look almost artificial. It is not proof, not yet, but it is enough to change the question forever. Before we go deeper into this journey, take a moment to subscribe and follow the channel, because what you're about to explore isn't just science. It's a story about where we come from, what might exist beyond us, and what it means to be alive in a universe that may not be empty at all. The image lingers in the mind, a world hundreds of billions of kilometers away, quietly orbiting its star, possibly holding the same ingredients that gave rise to life on Earth. And with that image comes a cascade of questions, ancient, persistent, and deeply human. Is life common in the universe, or are we a rare accident? Are there other civilizations looking back at the stars just as we are? And if they exist, why is the universe so silent? This silence forms the heart of what scientists call the Fermi paradox. In a universe so vast, filled with countless stars and planets, logic suggests that intelligent life should not only exist, it should be everywhere. And yet, we hear nothing. No signals, no clear evidence, just silence stretching across the cosmos. But the silence has not stopped the search. In fact, it has intensified it. Over the past few decades, a quiet revolution has taken place in astronomy. What was once speculation has become observation. Where there were once only theories, there are now discoveries. Hundreds at first, then thousands. Planets beyond our solar system, known as exoplanets, are no longer rare anomalies. They are everywhere. Our galaxy, the Milky Way, contains hundreds of billions of stars. And around many of those stars, planets orbit in the darkness. Some are massive gas giants, others are small and rocky, not unlike Earth. Some orbit too close to their stars, scorched by intense heat. Others drift too far away, frozen in eternal night. But a few, just a few, exist in a delicate balance. Scientists estimate that there may be around 30 billion planetary systems in our galaxy alone. Of those, perhaps half could contain planets similar in size and composition to Earth. That leads to a staggering possibility: around 15 billion Earth-like worlds scattered throughout the Milky Way. 15 billion chances for life. This number is difficult to comprehend. For most of human history, Earth was considered unique, the center of existence, the only known cradle of life. But that perspective is shifting. The more we observe, the more we realize that planets are not rare. They are the rule, not the exception. And if planets are common, then the conditions that gave rise to life on Earth might not be unique either. This realization changes everything. It means that somewhere out there, orbiting a distant star, there could be oceans under alien skies, continents shaped by unfamiliar forces, atmospheres filled with unknown chemistry. It means that life, perhaps simple, perhaps complex, could emerge wherever the right conditions align. And yet, despite these overwhelming numbers, despite the growing list of potentially habitable worlds, the silence remains. No confirmed signals, no undeniable evidence of intelligent life, just a vast, quiet universe filled with possibility. This tension between expectation and reality is what makes the search so compelling. On one hand, the numbers suggest that we should not be alone. On the other hand, the absence of evidence forces us to confront a more unsettling idea, that intelligent life may be far rarer than we imagine. Or perhaps it exists, but in forms we do not yet recognize. Or perhaps the distances are simply too great, the timing too misaligned. Civilizations may rise and fall across millions of years, never overlapping, never having the chance to communicate. Or perhaps they are out there, listening, just as we are, waiting for a signal that never comes. As telescopes become more powerful and detection methods more precise, we continue to refine our search. We look for subtle changes in starlight as planets pass in front of their stars. We measure tiny gravitational shifts that reveal unseen worlds. Each discovery adds another piece to the puzzle, another reminder that the universe is far more complex and far more populated than we once believed. But beyond the data and the equations lies something deeper. This search is not just about finding other worlds, it is about understanding our place among them. If life is common, then we are part of a vast cosmic tapestry, one thread among many. But if life, especially intelligent life, is rare, then our existence becomes something extraordinary. Not just a coincidence, but a responsibility. Because in a universe filled with billions of possibilities, we may be one of the few places where the universe has become aware of itself. And that realization brings us back to the beginning, to that distant image captured by a telescope floating silently in space. A faint blue world shimmering across the void. A question suspended in light. Are we looking at another Earth, or are we looking at a reflection of our own hopes, projected onto the stars? The answer is still out there, waiting. The question of whether we are alone does not begin in distant galaxies. It begins much closer to home, within our own solar system, where worlds once dismissed as lifeless are now revealing unexpected complexity. Among them, one stands out in both mystery and promise: Saturn's largest moon, Titan. At first glance, Titan appears hostile, a frozen world wrapped in a thick orange haze where temperatures plunge to nearly -200 degrees Celsius. But beneath that alien sky lies something extraordinary. Titan possesses a dense atmosphere, richer and thicker than Earth's in some ways, composed largely of nitrogen with traces of methane and other hydrocarbons. On its surface, there are lakes and seas, not of water, but of liquid methane and ethane, flowing and pooling like a strange mirror of Earth's own hydrological cycle. Rivers carve channels through icy terrain. Clouds gather and release methane rain. It is, in many ways, a familiar world built from unfamiliar chemistry. Yet the most intriguing possibility lies beneath the surface. Scientists suspect that deep below Titan's frozen crust, there may be a vast subsurface ocean of liquid water, hidden, insulated, and potentially stable over long periods of time. And where there is liquid water, even in darkness, the possibility of life begins to emerge. To explore this enigmatic world, future missions are being designed with remarkable ambition. A floating balloon drifting through Titan's dense atmosphere could travel for thousands of kilometers, scanning the landscape below. A lander, descending gently onto its surface, could analyze the composition of its lakes and soil. Together, these instruments would search for organic molecules, complex carbon-based compounds that are the building blocks of life, and assess whether Titan's chemistry has reached the threshold of prebiotic processes. Not life itself, perhaps, but the ingredients, the first steps on a long, uncertain path. While Titan captures attention with its eerie resemblance to Earth, another moon of Saturn presents an even more direct opportunity. Enceladus, smaller and brighter, appears at first to be nothing more than a frozen sphere. But along its south pole, something remarkable is happening. Vast jets of water vapor and ice erupt into space, forming towering plumes that extend hundreds of kilometers above the surface. These plumes are not random. They originate from cracks in the icy crust, fractures that connect directly to a global subsurface ocean. This ocean, unlike Titan's hidden depths, reveals itself in dramatic bursts, offering scientists a rare chance to study its contents without drilling through kilometers of ice. Spacecraft have already flown through these plumes, detecting water, salts, and organic molecules, key ingredients associated with habitability. The presence of heat, likely generated by tidal forces as Enceladus orbits Saturn, suggests that this ocean may be geologically active. Hydrothermal vents, similar to those found on Earth's ocean floors, could exist in its depths, providing energy and chemical gradients that sustain life. On Earth, such environments are teeming with microorganisms, life forms that thrive in complete darkness, independent of sunlight. If similar conditions exist within Enceladus, then the possibility of life is no longer speculative. It becomes a testable hypothesis. And yet, even in the most optimistic scenarios, any life that might exist on Titan or Enceladus would likely be simple, microbial, primitive, and vastly different from anything we might recognize as intelligent. These would not be civilizations, not cities or signals, but something more fundamental, evidence that life itself is not unique to Earth, that even in the cold, distant reaches of our own solar system, the process of becoming alive may begin wherever conditions allow. But if we are searching for more complex forms of life, organisms that evolve, adapt, and perhaps think, then we must look beyond our solar system to the stars themselves. The challenge, of course, is distance. Even the nearest stars are so far away that direct observation of their planets is extraordinarily difficult. We cannot simply point a telescope and see their surfaces in detail. Instead, we rely on indirect methods, subtle clues hidden in light and motion. One of the most powerful techniques is known as the transit method. When a planet passes in front of its host star, it blocks a tiny fraction of the star's light. This dimming is incredibly slight, often less than 1%, but with sensitive instruments, it can be detected and measured. By observing these periodic dips in brightness, astronomers can determine the planet's size, its orbital period, and even, in some cases, the composition of its atmosphere. Another method relies on gravity. Planets, though much smaller than stars, exert a gravitational pull that causes their stars to wobble ever so slightly. This motion, detectable through shifts in the star's light spectrum, reveals the presence of unseen companions. Through these tiny oscillations, entire planetary systems have been discovered. What these methods have revealed is astonishing. The first exoplanets detected were often massive gas giants, worlds larger than Jupiter, orbiting extremely close to their stars. These hot Jupiters defied expectations. According to earlier models, such planets should form far from their stars, where temperatures are low enough for gases to accumulate. And yet, there they were, completing orbits in just a few days, existing in environments once thought impossible. This discovery forced scientists to rethink everything they believed about planetary formation. It became clear that planets are not static objects, locked into place from the moment they form. They can migrate, shifting inward or outward over time, reshaping entire systems in the process. As detection methods improved, smaller and more Earth-like planets began to emerge from the data. Rocky worlds, some only slightly larger than Earth, orbiting within what is known as the habitable zone, the region around a star where temperatures allow liquid water to exist on the surface. These planets are of particular interest because they represent the best candidates for life as we understand it. Not too hot, not too cold, just enough energy to sustain chemical processes, but not so much as to destroy them. Each discovery adds another possibility, another world where oceans might exist, where atmospheres might form, where life might begin. And yet, even as the list grows longer, the deeper mystery remains unchanged. We are finding the places where life could exist. We are identifying the conditions that make it possible. But we have not yet found life itself, not beyond Earth. So the search continues, expanding outward, driven by curiosity, guided by science, and sustained by a question that refuses to fade. If the universe is filled with worlds like these, then somewhere, somehow, something must be alive. The only question is whether we will recognize it when we see it. If distant worlds can host the right conditions, and if oceans may hide beneath ice or methane skies, then a deeper question begins to surface, one that is even more fundamental than where life exists. It is the question of how life begins at all. To answer it, scientists have turned not only to telescopes and spacecraft, but to laboratories here on Earth. If the universe can create life, then perhaps the process can be understood, even recreated, in controlled conditions. And so, step by step, researchers have attempted to rewind the story of life back to its very first chapter. One approach has been to simulate environments beyond Earth, worlds like Titan, where chemistry unfolds under extreme cold and in the absence of liquid water at the surface. In carefully designed experiments, mixtures of gases such as nitrogen, methane, and carbon monoxide are cooled to temperatures that mirror Titan's atmosphere. Then, energy is introduced, sometimes in the form of electrical discharges, sometimes ultraviolet radiation, to mimic the influence of sunlight or cosmic energy. After days of reaction, something remarkable begins to appear. Dark, complex substances form, organic compounds that did not exist at the beginning of the experiment. These are not living organisms, but they are not simple molecules either. They occupy a space in between, intricate carbon-based structures that resemble the earliest chemical steps toward life. This process echoes one of the most famous experiments in modern science, conducted in 1953 by Stanley Miller. In his experiment, a mixture of gases thought to resemble Earth's early atmosphere, methane, ammonia, hydrogen, and water vapor, was exposed to electrical sparks, simulating lightning. Within days, the clear mixture transformed. Amino acids began to form, the essential building blocks of proteins, and by extension, of life itself. The result was both simple and profound. Under the right conditions, the basic components of life can arise naturally from non-living matter. But this is where the story becomes more complicated. Creating amino acids is not the same as creating life. These molecules are like bricks scattered across a landscape, useful, essential, but far from a functioning structure. Despite decades of research, no experiment has yet succeeded in bridging the gap between chemistry and biology, between molecules and organisms. The challenge lies in complexity. Life is not defined by a single molecule, but by systems, interconnected networks capable of metabolism, replication, and adaptation. DNA, the molecule that carries genetic information, is itself extraordinarily intricate. It cannot simply appear fully formed. It must emerge through a series of intermediate steps, each building upon the last. Scientists believe that the path from chemistry to life involved a gradual increase in complexity. It likely began with simple carbon-based molecules, formed in environments rich in energy and raw materials. These molecules interacted, combined, and recombined, forming larger structures, macromolecules capable of more sophisticated behavior. At some point, one of these structures gained a crucial ability, the capacity to replicate itself. This moment, when a molecule can produce copies of itself, is often considered the true beginning of life. Not because it is complex, but because it introduces something entirely new: continuity. A system that can persist, evolve, and respond to its environment over time. From that point forward, natural selection takes over. Variations emerge. Some structures are more stable, more efficient, more adaptable. They survive. Others disappear. Over vast stretches of time, this process leads to increasing complexity, eventually giving rise to cells, organisms, ecosystems, and, much later, intelligence. But for this process to begin, certain conditions must be present. Across all current theories, three elements appear consistently. First, carbon. Its unique ability to form stable, diverse bonds makes it the backbone of complex chemistry. Without carbon, the architecture of life as we know it would not be possible. Second, liquid water. not just as a solvent, but as a medium where molecules can move, interact, and react. Water provides the flexibility and stability needed for chemical evolution to proceed. Third, energy. Whether from sunlight, geothermal activity, or chemical gradients, energy drives the reactions that transform simple molecules into complex ones. Where these three elements coexist, the potential for life exists, not as a certainty but as a possibility. And yet, even if life begins under similar conditions elsewhere, there is no reason to assume it will look anything like life on Earth. Because if there is one lesson our own planet teaches us, it is that life is astonishingly adaptable. On Earth, life thrives in environments once thought uninhabitable. Deep beneath the ocean, where sunlight never reaches, organisms cluster around hydrothermal vents, surviving on chemical energy released from the planet's interior. In acidic lakes, in frozen glaciers, in the crushing pressure of the deep sea, life persists, adapts, and evolves. There are microbes that can endure extreme heat, others that survive intense radiation, and some that remain dormant for thousands of years, waiting for conditions to improve. These organisms, known as extremophiles, expand our understanding of what life can tolerate and where it might exist. If life can adapt to such extremes on Earth, then the range of possible habitats in the universe expands dramatically. But adaptation does not only affect where life exists, it also shapes how life appears. On Earth, plants are green because they reflect green wavelengths of light, absorbing others for photosynthesis. But this is not a universal rule. It is simply an adaptation to our sun's spectrum. On a planet orbiting a different type of star, where the dominant wavelengths of light differ, photosynthetic organisms might evolve entirely different colors. Under a bluer star, vegetation could appear dark or even black, absorbing as much energy as possible. Around a cooler star, it might reflect different hues entirely. Similarly, the structure of life could vary depending on environmental conditions. On a planet with stronger gravity, organisms might be shorter, more compact, built to withstand the force pulling them downward. In a world with dense atmospheres, flight might be easier, leading to entirely different evolutionary paths. Even the basic chemistry of life could differ. While carbon is the most likely foundation, alternative biochemistries have been proposed. Life based on silicon or utilizing solvents other than water, such as methane or ammonia. All of this leads to a critical realization. We cannot assume that life elsewhere will resemble life here. The mistake would be to search only for what is familiar, to expect faces, forms, or ecosystems that mirror our own. The universe does not follow human expectations. It follows physical laws, and within those laws, it explores possibilities far beyond our imagination. So when we search for life beyond Earth, we are not just searching for copies of ourselves. We are searching for something more abstract, more fundamental, a pattern, a process, a signature that indicates complexity, organization, and change. Something that is not random, something that is alive. And perhaps, when we finally find it, it will not be what we expected at all. If life can begin from chemistry, and if it can adapt to the harshest environments imaginable, then the next question rises almost inevitably. Does life, given enough time, learn to think? Not just to survive, but to observe, to question, to look up at the sky and wonder as we do. On Earth, this transition, from simple organisms to intelligent beings, took billions of years. It required stability, evolution, and a series of unlikely steps. The emergence of complex cells, multicellular life, nervous systems, consciousness. Intelligence, it seems, is not the default outcome of life. It is a rare trajectory shaped by chance as much as necessity. To understand how often this might happen elsewhere, scientists developed a framework, not to provide exact answers, but to organize uncertainty. It is known as the Drake equation. Rather than a single number, it is a chain of factors. How many stars form each year? How many of those stars have planets? How many planets could support life? How often does life actually emerge? And once it does, how often does it evolve into intelligence? Finally, how long do such civilizations last? Each term introduces uncertainty. Some can be estimated with data. Others remain almost entirely unknown. Depending on how these values are chosen, the results vary dramatically. In a pessimistic scenario, the chain breaks early. Perhaps life rarely begins, or perhaps intelligence almost never develops. In that case, the equation yields a sobering conclusion. We may be alone, not just in our galaxy, but perhaps in the observable universe. A single instance of awareness, isolated in an immense cosmic void. But in a more optimistic scenario, the numbers shift. Life emerges frequently. Intelligence evolves under the right conditions. Civilizations arise across the galaxy, separated by distance, but not by rarity. In this view, there could be hundreds, even thousands, of technologically advanced societies scattered among the stars. Two radically different possibilities, both consistent with what we currently know. And yet, regardless of which scenario we consider, one question refuses to disappear. If intelligent civilizations are common, where are they? This question, simple in form but profound in implication, is known as the Fermi paradox. It captures the tension between expectation and observation. The universe is vast, ancient, and filled with planets. By all reasonable estimates, there has been more than enough time for intelligent life to emerge, not just once, but many times. Some of these civilizations, if they exist, would be millions of years older than ours. With such a head start, their technology could be far beyond anything we can currently imagine. They might have explored their star systems, expanded across interstellar space, or developed methods of communication we have yet to conceive. And still, we see nothing. No clear signals, no artifacts, no undeniable traces of their existence. The silence remains. To explain this, many possibilities have been proposed. Perhaps intelligent life is extraordinarily rare, a fragile outcome that almost always fails to persist. Civilizations may arise, but they may also destroy themselves through war, environmental collapse, or technological risks before they can spread beyond their homeworlds. Or perhaps the universe is filled with life, but it is separated by distances so vast that communication becomes impractical. Signals weaken over light years. Travel between stars requires immense energy and time. Civilizations may exist in isolation, each confined to its own region of space. There is also a more subtle possibility. Advanced civilizations may not behave in ways we expect. They may choose not to broadcast their presence, or they may communicate using methods we cannot yet detect. To us, the universe appears silent, not because it is empty, but because we are listening in the wrong way. To explore these ideas further, scientists have imagined a scale of technological development known as the Kardashev scale. A Type 1 civilization harnesses the full energy of its home planet, controlling weather, oceans, and global resources. Humanity is not yet at this level, but we are approaching it. A Type 2 civilization extends its reach to its star, capturing a significant fraction of its energy output, perhaps through massive structures that surround the star itself. A Type 3 civilization operates on a galactic scale, utilizing the energy of billions of stars. These categories are not predictions, but possibilities, ways of imagining how intelligence might evolve over cosmic timescales. And if such civilizations exist, their presence might be detectable, not through direct contact, but through the signatures of their energy use. So far, we have not found definitive evidence of any, but the search continues, not only through observation of distant stars, but through a more direct approach, listening. For decades, scientists have been engaged in a quiet effort to detect signals from other civilizations. This effort is known as SETI. Using radio telescopes, SETI scans the sky for patterns, signals that stand out from natural cosmic noise. The idea is simple. While stars, galaxies, and other astronomical objects produce radio waves, these emissions follow predictable patterns. A signal that is narrow, structured, or repeating in a deliberate way could indicate an artificial origin. So far, no confirmed signal has been found. There have been intriguing moments, brief detections that sparked excitement, but none have withstood rigorous verification. Each time, the signal either could not be repeated or was eventually traced back to natural or human-made sources. Still, the possibility remains. If a signal were to be detected, what would it look like? One of the simplest forms would be a sequence of binary code, patterns of ones and zeros that could encode information. Mathematics, after all, is a universal language. A sequence based on prime numbers, for example, would be unlikely to arise from natural processes and could serve as a clear indicator of intelligence. More complex signals might contain structured data, images, diagrams, or symbolic representations. In 1974, humanity itself attempted such a transmission, sending a message from the Arecibo radio telescope toward a distant cluster of stars. The message included basic information about human biology, our solar system, and our position in the galaxy. If another civilization received it, and if they chose to respond, the reply would take tens of thousands of years to arrive. Communication, on cosmic scales, is not a conversation. It is a slow exchange across generations. And if a signal were detected today, the response would not be simple or immediate. There are protocols in place, developed by the scientific community, to guide such a moment. First, the signal must be verified, confirmed by independent observations to rule out errors or interference. Only then would the discovery be announced, shared openly with the global community. No single nation would own it. No government could claim it. It would belong to humanity as a whole. Because such a discovery would not just answer a scientific question, it would redefine our understanding of ourselves. It would mean that somewhere, across the vast distances of space, another form of intelligence has emerged, another mind capable of observation, of communication, of wondering about the universe, another presence in the silence. And in that moment, the question would no longer be whether we are alone. It would become something far more complex. What do we say back? If one day a signal does arrive, clear, undeniable, and unmistakably artificial, it will not just answer a scientific question. It will force us to confront something deeper, something philosophical, something that has been quietly waiting beneath every equation and telescope observation. Because until that moment comes, we are left with two possibilities, and both are equally unsettling. The first is that we are alone, not just temporarily alone or geographically isolated, but fundamentally alone in the observable universe. A single instance of intelligent life emerging from billions of years of cosmic evolution, surrounded by silence that is not temporary but absolute. No other civilizations, no other minds looking back at the stars, just us. At first, this idea feels improbable. The universe is too vast, too rich in possibility. But probability is not certainty. And if it is true, if life is so rare that it has happened only once, then our existence becomes something almost beyond comprehension. Every thought, every culture, every piece of knowledge humanity has ever produced would represent the only known expression of awareness in the universe. We would not just be observers of reality, we would be its only witnesses. And that carries a weight that is difficult to ignore, because if we are alone, then everything depends on us. The survival of intelligence, the preservation of knowledge, the continuation of conscious experience, these are no longer shared responsibilities across a cosmic community. They are ours alone to protect or to lose. But there is another possibility, that we are not alone, but we are early, that somewhere in the future, across thousands or millions of years, other civilizations will emerge. That intelligence is not unique, but simply rare in time, and that we happen to exist near the beginning of that timeline. In this scenario, we are not the only voice in the universe, we are the first. And that changes the meaning of our existence in a different way, because being first is not just a position, it is a responsibility. If life is destined to spread, to move beyond its planet of origin, to carry awareness across the stars, then the first civilization to reach that point becomes something more than a species. It becomes a bridge between a silent universe and one that is awake. In that sense, humanity's future is not just about survival, it is about continuity, about whether we choose to remain confined to a single world, vulnerable to its limits, or whether we extend beyond it, becoming a part of the larger cosmic story. Either way, whether we are alone or simply first, the conclusion is the same. What we do next matters, because the universe, for all its vastness, is not a safe place. Long before humanity existed, Earth has faced forces capable of reshaping or even ending life entirely, and those forces have not disappeared. They remain quiet, distant, often invisible, but always present. One of the most immediate and well-understood threats comes from objects much smaller than planets, yet powerful enough to alter the course of life. Asteroids. Among them is Apophis, a near-Earth asteroid that once raised concern due to its potential close approaches. While current observations indicate that it poses no significant impact risk in the foreseeable future, it serves as a reminder of a larger reality. Earth exists in a dynamic environment where objects move unpredictably over long timescales. The history of our planet includes impacts far more catastrophic than anything recorded in human memory. Events capable of triggering global climate change, mass extinctions, and the collapse of entire ecosystems. Today, however, we are no longer passive observers. We are developing methods to detect and potentially deflect such threats. By tracking asteroid trajectories, we can identify risks decades in advance. Proposed solutions range from kinetic impactors, spacecraft designed to collide with an asteroid and alter its path, to more complex strategies involving gravitational influence or controlled fragmentation. For the first time in history, a species has the ability to prevent a natural extinction-level event. But not all threats are so manageable. Some originate not from nearby space, but from the deeper, more violent processes of the universe. Among the most powerful are gamma-ray bursts, intense flashes of high-energy radiation produced by extreme cosmic events, such as collapsing massive stars or the merging of neutron stars. These bursts release, in seconds, more energy than the Sun will produce over its entire lifetime. If one were to occur close enough to Earth and be directed toward us, the consequences could be severe. The planet's atmosphere could be stripped or chemically altered, ozone layers disrupted, and surface life exposed to lethal radiation. Such events are rare on human timescales, but across millions of years, their probability is not zero. Closer to home, Earth's own protective systems are not permanent. The planet is shielded from harmful solar and cosmic radiation by its magnetic field, a vast, invisible structure generated by the movement of molten iron within its core. This field deflects charged particles, preserving the atmosphere and protecting life at the surface. But this magnetic field is not constant. Over geological time, it has weakened, shifted, and even reversed entirely. Magnetic pole reversals have occurred many times in Earth's history. During these periods, the field does not disappear completely, but it becomes more complex and less stable, potentially allowing increased radiation to reach the surface. The full biological impact of such reversals is still debated, but they remind us that even the systems we rely on most are subject to change. Then there are slower, more subtle forces, cycles that unfold over tens of thousands of years, gradually reshaping the planet's climate. Ice ages, driven by variations in Earth's orbit and axial tilt, have transformed landscapes, lowered sea levels, and altered ecosystems on a global scale. These cycles are natural, but they are not isolated. Human activity, particularly the emission of greenhouse gases like carbon dioxide, has begun to influence the planet's climate in ways that may interact with these long-term patterns. The result is a system that is both natural and altered, predictable in some ways, uncertain in others. And beneath it all, deep within the Earth, another force waits: supervolcanoes. Unlike ordinary volcanic eruptions, these events release enormous volumes of ash and gas into the atmosphere, capable of blocking sunlight and triggering global cooling. The effects can last for years, disrupting agriculture, collapsing food chains, and reshaping life on a planetary scale. Such eruptions are rare, but they have happened before, and they will happen again. Taken together, these threats, asteroids, radiation bursts, magnetic shifts, climate cycles, geological upheavals, paint a picture that is both humbling and urgent. Life on Earth has survived them before, adapting, evolving, recovering. But survival has never been guaranteed. Extinction, too, is part of the story. The difference now is that, for the first time, one species understands the risks. We can observe them, model them, prepare for them. In some cases, we may even prevent them. But awareness alone is not enough, because the question is no longer just whether life can survive. It is whether intelligent life, capable of understanding its place in the universe, can endure long enough to become something more. Long before humanity learned to map the stars or imagine distant worlds, life on Earth had already endured a series of trials so severe that, by any reasonable measure, it should not have survived at all. And yet, it did. Not once, but again and again, through collapse, through silence, through near total erasure. The history of life is not a smooth progression. It is a story written in cycles: growth, disruption, extinction, and renewal. Scientists have identified 5 major extinction events in Earth's past, each one reshaping the trajectory of life in profound and irreversible ways. These were not gradual declines. They were sudden, catastrophic disruptions that eliminated vast portions of the planet's biodiversity in relatively short periods of time. The first of these occurred over 400 million years ago during the late Ordovician period. At the time, life was concentrated in the oceans, diverse and flourishing. Then, a rapid cooling event triggered a global glaciation. Sea levels dropped, habitats vanished, and a large percentage of marine species disappeared. The oceans, once full of life, became quiet, but not empty. From what remained, life began again. New species emerged, adapted to the changed environment, filling ecological niches left behind by those that had vanished. The second great extinction, in the late Devonian, unfolded more gradually but with equally devastating consequences. Changes in climate, ocean chemistry, and possibly the spread of land plants disrupted marine ecosystems. Coral reefs collapsed. Entire groups of organisms declined. Again, life contracted, then slowly expanded into new forms. The third extinction, at the end of the Permian period, stands as the most severe known event in Earth's history. Often called the Great Dying, it wiped out an estimated 90% of marine species and a significant portion of life on land. The causes are still studied, but massive volcanic activity likely played a central role, releasing enormous quantities of greenhouse gases and triggering extreme climate change. For a time, the planet must have seemed almost lifeless, and yet, even then, life persisted. From the remnants of that collapse, ecosystems rebuilt themselves. New lineages evolved, setting the stage for the rise of entirely different forms of life. The fourth extinction, at the end of the Triassic period, cleared the way for the dominance of dinosaurs. And the fifth, perhaps the most well-known, occurred 66 million years ago, when a massive asteroid struck Earth, altering the climate and bringing an end to the age of dinosaurs. This event is often associated with an impact near what is now the Yucatan Peninsula. The collision released immense energy, sending debris into the atmosphere, blocking sunlight and disrupting global ecosystems. Large animals, unable to adapt quickly, disappeared, but small, adaptable organisms survived. Among them were early mammals, creatures that would eventually give rise to us. Each extinction event followed a similar pattern: destruction on a massive scale, followed by a slow and uncertain recovery. Species vanished, ecosystems collapsed, but life itself endured. Not unchanged, not untouched, but persistent. This dual nature of life, its fragility and its resilience, is one of its most defining characteristics. It can be erased from entire regions, reduced to isolated pockets, pushed to the brink of disappearance. And yet, given time, it returns. It adapts. It evolves. It begins again. This pattern carries an important implication. Life is not guaranteed to continue in any specific form. The species that exist today, including humans, are not permanent features of the planet. They are temporary outcomes of an ongoing process. Extinction is not an anomaly. It is part of the system. But so is renewal. And that brings us back to the present, to a moment unlike any other in Earth's history. For the first time, a species exists that can not only experience these cycles, but understand them. A species that can look into the past, recognize patterns, and attempt to influence the future. We are not outside the system. We are part of it. But we are also something new within it. When we step back and consider the broader picture, the scale of the universe, the abundance of planets, the emergence of life, the rarity of intelligence, and the repeated cycles of extinction and recovery, a clearer perspective begins to form. The universe is vast beyond comprehension. Galaxies stretch across billions of light years, each containing billions of stars, many of which host planets of their own. Within this immense structure, the conditions for life may arise in countless places. Life, in its simplest forms, may not be rare at all, but intelligence, the ability to reflect, to question, to understand, may be far less common. It requires not only the right conditions, but time, stability, and a series of unlikely transitions. We may not be unique, but we may be uncommon. And that distinction matters, because it means that while we are not the center of the universe, we are still significant within it. Not because of where we are, but because of what we are capable of. We are a way for the universe to observe itself, to become aware, even if only in a small and fragile corner of its vast expanse. This does not place us above the rest of existence, but it does give us a role, a responsibility, to preserve what has emerged here, to understand it more deeply, and perhaps, one day, to carry it beyond the limits of this single planet. But such goals are not immediate. They unfold over generations, over centuries, perhaps over millennia. And so, for now, the most important quality is not speed, but patience. The search for life beyond Earth continues. Telescopes grow more powerful, missions venture farther, data accumulates, patterns emerge. We do not yet have all the answers. But that does not mean the answers are not there. Somewhere in the vastness of space, light is traveling toward us, signals that began their journey long before we existed. Within that light may be information we have not yet learned to read, evidence we have not yet learned to recognize. The universe does not rush to reveal itself, it waits. And one day, whether through a faint atmospheric signature on a distant planet, a chemical imbalance that suggests biology, or a signal that carries the unmistakable mark of intelligence, we may finally find what we have been searching for. When that moment comes, it will not just be a scientific discovery, it will be a turning point. Because the question that has followed humanity for as long as we have looked at the stars, are we alone, will finally have an answer. And whatever that answer is, it will change us. Not gradually, not subtly, but permanently.